Let's begin with defining the term impulse and momentum. First is we define momentum. What is momentum? A momentum is the mass of an object and its velocity. So literally speaking, that momentum is all about a moving object's mass. So when an object moves, because we believe that every object in the universe has mass and occupies space, and whether that object is moving from one point to another point, the object gains its momentum. Since it started from rest, then it moves from one position to another position. So hence, if that particular phenomenon happened, our object experiences momentum. Now, momentum is defined in a very technical way. In layman's terms, momentum is just the mass and the object's velocity. But in physics, technically speaking, in physics, we define momentum as the product of mass and momentum, which is defined or represented by a small letter p. Why p? So that we won't be confused with the representation of power with capital P. Now, remember that momentum is always a vector quantity. And it is because of one variable, velocity v. Remember that v is written as v with an arrowhead on top. Because v is a vector quantity, it has both magnitude and direction. Now, what makes momentum a vector quantity? Simply because momentum is moving. Imagine you are moving in a straight line. You have mass. You are moving in a straight line going north. So you have magnitude, you're going in a straight line, and you are directed north. So you have both magnitude and direction. So momentum in that sense, since you are moving going north, then the momentum of the body is also going north. Hence, momentum is also defined as a vector quantity due to the velocity of the object. And as you notice, that P, momentum P, also has an arrowhead on top of it. Since mass is a scalar quantity, we do not write an arrowhead on top of it. So P is defined as the product of mass and momentum. If the object stops moving, what could be the reason behind? We think of it in a way that someone or something must have stopped the object. So that term stop there, what could it be? What causes the object to stop? Hence, we can describe another term in physics. We call it as impulse. Technically speaking, impulse is the product of force and time acting upon an object. And if we exert force to an object, it's either it will accelerate, or it will decelerate, or even it will stop, right? Following Newton's second law of motion, the law of acceleration, wherein the object will accelerate if there is an external force applied to it. F is equal to ma, right? But in impulse, we also define impulse as a change in momentum. And then later, we will be talking about how does impulse become a change in momentum. Okay. Impulse is defined as force, as a product of force and time. Since it's a product of force, impulse is denoted as capital J. J, in some university physics books, it's denoted as J. In some physics books, it's denoted as I. But I'm more comfortable in using J. And F stands for the force, which has a unit of newtons, and T stands for the time. So if we multiply these two, we have the value of impulse. And remember that impulse is also a vector quantity. And what makes impulse a vector quantity is only because of one variable, which is our force. Remember that the force is a vector quantity. And how do we find force? Using the second law of motion, F is equal to ma. Mass has a unit in kilograms. Acceleration has a unit of meters per second square. Why meters per second square? Because acceleration is a product of the change in velocity v. We have delta x all over time. And how did we come up with meter per second square? Because velocity is a product, is a quotient of distance and time, which is meters per second, and we divide it by time, which has a unit of seconds. Then if we simplify it, it will become meter per second, or just simply as meter per second squared. There are 2 seconds in the denominator. Now, we believe that impulse and momentum are related with each other. And there is a connection between these two variables, impulse and momentum. How? How are they related? According to the Impulse-Momentum Theorem, it states that when an object changes its linear momentum or its momentum, we are always assuming that it is caused by a force. And what variable does the force is affecting it? Okay. We have the term impulse. So if there is a change in momentum of the object, then there should be a force applied to the object. And if there is a force applied to the object in a certain period of time, then there should be impulse. So if there's a change in momentum, there is also change, or there should also be an impulse applied to the object. And if both are present, then we can assume that this change in linear momentum is caused by the impulse. And hence, we define Impulse-Momentum Theorem as I is equal to delta P, wherein the impulse J, or J is equal to delta P, where impulse J is equal to the amount, whatever would be the amount of change in the linear momentum of the object, should be the same with the impulse applied to the object. Now, how were we able to prove that impulse J and delta P is the same? We can play these two equations using dimension analysis. J stands for what? Impulse, and it has a unit of Newton seconds. So Newton seconds is equal to delta P. Delta P is, say, if there is a change, then there should be the difference between two variables. So there should be an initial momentum and a final momentum. So since it's a change, so it should be the difference between the initial and the final. So we can write here as P minus P naught. And the unit of P is kilogram meter per second. So we can write here Newton seconds is equal to kilogram meter per second minus kilogram meter per second. So if we subtract kilogram meter per second by kilogram meter per second, that will give us just the same unit. It's just kilogram meter per second. So I can just write here kilogram meter per second. But what about Newton seconds? Newton, 1 Newton is 1 kilogram meter per second. So we can write here seconds kilogram meter per second square, right? So there's another second here. So what can we do is that we can simplify kilogram meter per second square times second. So how can we simplify this? Remember, this meter per second per second. So there are 2 seconds, there are 2 units of time in the denominator. So what we can do is that we can multiply kilogram meter per second square and second, so that the second square will cancel out. That will give us kilogram meter per second. Okay, because there are 2 seconds in the denominator, and if we cross multiply it, that will give us kilogram meter second divided by meter second square. So if meter, this will turn into kilogram meter second all over second square. If we simplify seconds, second divided by second square, that will give us meter per second. This will cancel out. So we can have here kilogram meter per second is equal to kilogram meter per second. So hence, we were able to find out that impulse is the same with a change of momentum. So they are equal with each other. So we were able to prove using dimension analysis that Impulse-Momentum Theorem is correct when there is a change of impulse, or it is caused by an impulse that caused the change in the momentum of the object. So how does the object changes its momentum? First is, it's either it started from rest, then it starts moving. That's first case, because what's your speed when you are at rest? So just equal to 0. So hence, you have a 0 momentum. If you move, you gain velocity, you're moving already. What's your momentum? That's equal to a non-zero momentum. So you have a change in momentum already. You have an initial and you have a final. That's case number 1. Case number 2 is that when you are stopped by a force, where impulse momentum comes in. Now, how do we simplify impulse momentum theorem? We can use the second law of motion, the law of acceleration by Isaac Newton, where we can show the relationship, we clearly can show the relationship between impulse and momentum, because we believe that impulse and momentum are directly equal or related with each other, right? We have J is equal to delta P, wherein J is equal to Ft, right? So Ft is equal to P, and P is what? Mass times velocity. Now, using that proof, using that reasoning, we can just justify using this law of motion, the law of acceleration. How? First is we need to write the first law of motion. We have F is equal to ma, right? And then A is acceleration, is a derived quantity, and it is defined as the change in the object's velocity per unit time. So we have A is equal to V minus V naught all over T. We also have, so what we can do here is that we can substitute A with this equation. This equation will substitute A, because A is equal to V all over T, or delta V all over T. So if we substitute it, we can have F is equal to M times the quantity of delta V all over T. Now, how our goal is, it should be Ft is equal to M delta V, because delta V is the only thing, the only indicator that would allow us to see that there is a change in momentum, right? Because there's the velocity changing, the mass doesn't change because it's a scalar one, it's a constant one, right? So what are we going to do? What we can do here is that we will be equalizing the equation by moving T from this side to this side. And how do we do that? What we can do is that we can multiply both sides by t. Whatever I'm going to do on the side of the equation, I must do on the other side. So it can be equalized. So if I'm going to multiply both sides with t, the t here will cancel out because t divided by t, that's equal to 1. This will cancel out. Hence, we have ft is equal to m times the quantity of delta v, which is v minus v naught. So we have here impulse and the change in momentum. So using the second law of motion, we can define easily the impulse-momentum theorem that impulse is the same with the change in momentum. So when the object changes its momentum, the object also experiencing an impulse. Let's have a quick recap on the definition of linear momentum before proceeding to the problem. Remember that linear momentum is defined as the object's mass and its product with velocity. So we have two variables that should always be present before finding out the momentum of the object. You should have the object's mass and its velocity. And momentum is mathematically defined as the product of mass and velocity. So assuming that an object is weighing on a certain mass of say that particular object weighs 2,500 kilograms. So let's assume that it's a truck. It's a big truck that weighs 2,500 kilograms. And that particular truck is moving very fast at a speed of 25 meters per second going north, say for example. What is the momentum of the object if it has this particular speed of 25 meters per second? According to our equation, P is equal to mv. We multiply mass and velocity of the object. So how do we multiply it? So first is we write the given variables. We have the mass, which is 2,500 kilograms, and the velocity, 25 meters per second. So we substitute m with 25 kilograms and 25 meters per second. Then we multiply the two variables, mass and velocity. So 25,000 or 2,500 or 2,500 multiplied by 25, that will give us a product of 62,500. And the unit is, we also multiply kilograms and meters per second. That will give us kilogram meter per second. So the truck's momentum is around 62,500 kilograms when it is moving at 25 meters per second. So if the object moves less than 25 meters per second, then you should also expect that the momentum also decreases because you decrease the velocity. If you increase the velocity, the momentum also increases because momentum and velocity are directly proportional with each other. So if you increase something on the velocity, then the momentum also increases. If you decrease the velocity, the momentum also decreases. For impulse-momentum theorem problem, it is somehow like a combination between two variables, momentum and impulse. So assuming, let's say for example, that a man that weighs 80 kilograms is running at 20 meters per second. So for the total duration of its particular motion running at 20 meters per second, he stopped for a particular time. Okay? After 10 seconds, he stopped. So on that particular scenario, we were able to describe the motion that an 80-kilogram man is running at 20 meters per second, but after 10 seconds of running at 20 meters per second, eventually that man stopped. So if the man stopped, then there should be a factor that allows the man to stop. And it has what? There should be a force applied to the man. Right? It's is either the force applied to the man is that he or she collided with a barrier, say for example, or whatever, that should have a force. There should be an external force applied to the object so that it will change its acceleration, right? It will change its acceleration. If you change the acceleration, the velocity also changes, and so on and so forth. So we can use the second law of motion description that we use in identifying or proving the impulse-momentum theorem. Ft is equal to m delta v. And how do we do this? So we can write Ft is equal to m v minus v naught. Okay, and we identify here the different possible variables that are present. We have the mass, which is 80. We have the initial velocity of 20 meters per second. That man is still running at 20 meters per second, right? And we also have the time interval t and the initial velocity, after the final velocity rather, of 0 meters per second. So the question is, how much force was applied to the object that allows him or caused him or her to stop? So what we're trying to look for is the force applied to the man or to the woman that is running at 20 meters per second for 10 seconds. Now, we have here our equation Ft is equal to mv. So since we're looking for F, the force, what we can do is that we can place t on the other side of the equation. We can do it by dividing both sides with t. So whatever I'll do on this other side of the equation, I should also do on the other side of the equation so that it will be equalized. This will cancel out. That will give us, this is equal to 1. That's canceled out. That will give us F is equal to m times the quantity of v minus v naught all over t. Notice that this is the original form of what? The second law of motion. This is just equal to m is equal to Fa. Now, we substitute or we plug in all the given variables. So we have 80 kilograms for the mass. We also have the final velocity, 0, and the initial velocity, 20. And of course, the time of 10 seconds. So what are we going to do is that we simplify first what is inside the parentheses. So we have here 0 minus 20. That will give us a negative 20, right? Then we multiply it by 80. So 80, multiply it by a negative 20. So 8 times 2 is 16. Then there are 2 zeros. So 16 plus 0 plus 0 in terms of for the decimal places. So we add the 2 zeros. We put it together. So we have 1600. So that's 1600. What about the negative sign? We should also include the negative sign. That's the negative 1600 kilogram meter per second. And then we divide it by 10 because that's time. That will give us kilogram meter per second. That we should note already that we are looking for the force, which is in newtons. So 1600 or 1600 divided by 10, that will give us negative 160 newtons. You should not forget the negative. And this is the final answer. This is negative 160 newtons. But I wanted to write in a vector form. So I can get the absolute value of negative 160, that is equal to 160 newton. And of course, this is the magnitude of the force. Remember that the force is a vector quantity. It has both magnitude and direction. So on what particular direction is the force applied? Since it is negative, it's a negative 160, that would give us the idea that the force applied to the object, which is 160 newtons, was applied in an opposite direction. So if this man is running on this side, is going towards here, then the force applied to this guy should be here. Okay? It should oppose the direction of the motion. So what happens if we oppose the direction of the motion? Then there should be an impulse applied to the object that should cause the deceleration or the stopping of the object's motion.